In this example, which is example 6.3 from the notes, we'll apply linear least squares regression to fit a model of enzyme kinetics to some experimental data. This model is derived by assuming that there's a reversible reaction between a substrate and an enzyme to form an enzyme-substrate complex, which in a second step decomposes irreversibly to a product and the free enzyme. This results in a kinetic expression for the rate of production of the product shown here. If the enzyme-substrate complex formation is a rate-limiting step, that is, the rate coefficient K1 times the concentration of enzyme is much less than the rate coefficient K2, and the reverse reaction rate coefficient K minus 1 is much less than K2, then an approximate form of this rate law can be derived, which is pseudo first order in the substrate concentration C1. Therefore, the rate is a linear function of the substrate concentration. In the example in the text, these data are fit using linear least squares regression to obtain the pseudo first order rate coefficient K1 prime. When performing the linear least squares regression, we fit the data to a model that contains a slope and an intercept, even though the model predicts that the intercept should be 0. The reason we want to do this is because when performing the fit, the parameter K1 prime here determines how the rate of product formation changes when the concentration of CS changes. If we constrain the fit so that we force the intercept of the fit to be 0, then we have to relax one of the two equations that we used for the linear least squares regression. Graphically, forcing the fit to go through the origin would overestimate the slope K1 prime and assume that we know that this approximate model is valid near the origin when in fact we have no data at the origin. It could be that our experimental data measuring the reaction rate contains some offset or bias in it due to an error in the experimental measurement, such as an instrument calibration. If we force the fit to go through the origin at 0, 0, then that offset would bias our solution for K1 prime. Generally, when performing linear least squares regression on a model like this that has no intercept, you should include the intercept as an adjustable parameter. In this case, we used a simplified version of the model that was linear, but what if our model y hat of x is nonlinear? In many cases, we can linearize nonlinear models. The model on the previous slide describes what we call Machaelis-Menten kinetics, which gives rise to a saturation type equation. Here, the independent variable is CS, and here the independent variable is x. Rather than making assumptions about the rate coefficients, we can linearize a saturation model by a transformation of variables. If we define u as the reciprocal of x and v as the reciprocal of y, then the relationship between u and v is a linear relationship. We can derive this by taking the reciprocal of the nonlinear form of the equation. Nonlinear power law saturation models can also be linearized by taking the natural logarithm of the equation. The corresponding transformed u and v variables in the linear form are shown here. Many exponential models can also be linearized by taking the natural log. Here, the variable transformation is u is equal to x and v is equal to the natural log of y. Power laws can also often be linearized by taking a natural log. Let's consider again the enzyme kinetics, and this time assume that the enzyme substrate decomposition is rate limiting. That is, K1 times the concentration of enzyme is much greater than K2, and the reverse reaction rate coefficient is much greater than the decomposition to form the products. In this case, we can rewrite the rate law using an equilibrium constant capital K for the reversible formation of the enzyme substrate complex. This is a saturation model similar to the equation in the first row of the table on the previous page. If we transform the variables representing the concentration of the substrate and the rate of product formation by taking the reciprocal, this equation is linearized in the unknown coefficients. The intercept is the reciprocal of k2 prime, and the slope is the reciprocal of k times k2 prime. Now we can fit the transformed data to a line using linear least squares regression to extract these coefficients.